Good morning to all of you. Today we will continue with our discussion on electrostatics. Let us recall that in the last lecture we had discussed about capacitance and capacitors. So, let me recall, a capacitance is a device which consists of two conductors which are separated by a dielectric or air and carrying equal and opposite charges. So, if you shift some electrons from one conductor to another conductor, then one of the conductors gets positively charged, the other conductor gets negatively charged, and they are separated by a certain distance, and this unit forms a capacitor. And this capacitance, as we will see, stores energy, electrostatic energy, which can be used for various purposes. And capacitors form a very, very important component of all electronic circuits. Charging of a capacitor means you take a capacitor and connect a battery to it, and in that process transfer electrons from one conductor to the other conductor, and that leads to a charging. And then if you disconnect your battery, then the capacitor remains charged. We had calculated, as an example, we started looking at a parallel plate capacitor. So, parallel plate capacitor consists of two plates of area A separated by distance d. So, let me draw a 3-dimensional figure here. So, there are two plates here, one plate here, another plate, and so you may have positive charges on the upper plate, the lower plate is negatively charged, and in between these two plates there is an electric field pointing like this. And so, area is of this plate is A and D is the separation. So, in this example the upper plate is carrying positive charge, the lower plate is carrying negative charge, and we had calculated the capacitance of this device. D is the separation between the plates, A is the area of the plates, and epsilon 0 is the permittivity of free space. And the unit of capacitance is farad, and you can see that farad is a unit which is, because C is Q by V, capacitance has coulomb per volt. 1 farad is 1 coulomb per volt. That farad comes from Michael Faraday's name, and that is the unit of capacitance. Farad is a very large capacitance. Typically in circuits we use microfarads or picofarads of capacitance. We are also looked at an example and shown that a typical capacitance you can get about 10 picofarads. Now, today what I want to do is to discuss some more examples of capacitance, and as the next example we will take a cylindrical capacitor. So, you can imagine a central conductor surrounded by another conductor in the form of a cylinder, and if I draw the cross section, I have the central conductor here and the outside conductor. So, let me draw a thickness of the outer conductor here. So, this is one conductor here, this is another conductor, and let me call this radius, they are coaxial. So, this is radius A and this radius is B. The outer radius, the radius of the inner conductor is A, the radius of the inner surface of the outer conductor is B. So, let me assume that the inner conductor is positively charged and there is an equal amount of negative charge on the outer conductor. So, what I need to calculate capacitance is a relationship between the voltage between the two conductors and the charge in the two conductors, because that proportionality constant gives me the capacitance. So, to calculate voltage I need to know the electric field. We have already done this before. So, for calculating electric field what I do is I take a Gaussian surface of radius r and of length L. So, if the cylinder is like this, if the inner conductor is here and outer conductor is like this, I will take a Gaussian surface of length L, this length L and of radius r from the center. So, and we have already discussed by symmetry arguments the electric field will be radial away from the center. So, and so there is no Gaussian flux, electric flux on the top and bottom surface of the cylinder of the Gaussian surface. There is only flux from the cylindrical surface. So, whose area is 2 pi r into L into electric field is a flux must be equal to the charge contained. So, if I assume that lambda is the charge per unit length, so the charge contained is lambda into L by epsilon 0. Lambda is the charge per unit length. So, so much length of the conductor contains lambda L charge. So, electric field becomes lambda by 2 pi epsilon 0 r. This we have already calculated before, and because the electric field is in the radial direction from the axis outwards, I can write the electric field as E is equal to this in r cap. So, that is the electric field on of the this configuration of one conductor, cylindrical conductor surrounded by another cylindrical conductor. Now, I need to calculate the potential difference between the outer and inner conductors. So, we know how to calculate potential differences. So, let me calculate the potential difference. V is equal to V of the inner conductor minus V of the outer conductor. So, which is equal to minus integral B to A E dot dr, which is equal to lambda by 2 pi epsilon 0 into A to B dr by r, which is equal to lambda by 2 pi epsilon 0 into log of V by A. So, that is the potential difference between the inner and outer conductors. So, the inner conductor is at a higher potential, it is positively charged. So, the inner conductor is at a higher potential compared to the outer conductor. Now, I want to write this in terms of the total charge. So, if I take a length L, the charge will be is equal to lambda into L. So, I replace lambda by q by L in this equation and I get the following equation: V is equal to q by 2 pi epsilon 0 L into log B by A. And so, because we know that V is equal to q by C, we can define the capacitance of this configuration. C is equal to 2 pi epsilon 0 L by log V by A. That is the capacitance of a length L of the of this cylindrical capacitor. We can define a capacitance per unit length is equal to C by L, which is equal to 2 pi epsilon 0 by ln of V by A. So, as you can see here, the capacitance only depends on the geometric parameters. For a parallel plate capacitor, it was epsilon 0 A by D. Here the capacitance per unit length, please remember this is capacitance per unit length of the cylindrical conductor, cylindrical capacitor, and the capacitance per unit length is given by 2 pi epsilon 0 by log V by E. Now, let me take some examples here. Let me take an inner radius of 2 millimeters, an outer radius of 4 millimeters, and so the capacitance C is equal to 2 pi epsilon 0 by ln b by a, which is equal to 2 pi into 8.85 into 10 to the minus 12 by ln of 4 by 2, and you can estimate this to be approximately equal to 80 picofarad per meter, which is actually 80 into 10 to the power minus 12 farad per meter. So, what it implies is, if you take 1 meter length of this cable of this cylindrical capacitor, it will have a capacitance of 80 picofarads. You must have seen such cylindrical conductors, cylindrical capacitors that are used for connecting television and VCRs through cables, and those cables are called coaxial cables. Have a typical capacitance of about 70 picofarad per meter. There are also insulators between the conductors there. So, we are right now assuming that the two conductors are separated by free space. So, that is an example of a cylindrical capacitor, and this capacitance which we have written here is the capacitance per unit length of the cylindrical capacitor. Let me take another example, a spherical capacitor. Spherical capacitor consists of one inner spherical conductor surrounded by an outer spherical conductor. The inner sphere is charged positively, assumed to be charged positively. The outer sphere is assumed to be charged negatively, and same charge is put on the inner and outer spherical conductor. Let me assume that the radius of inner sphere is equal to R A, and radius of outer sphere is equal to R B. So, as you can see here, there are electric field lines now going from positive to negative. So, I need to again, just like before, calculate the potential difference between the outer and inner conductor and find out how that is related to the charge contained in the capacitors in the conductors. So, let me assume the charges are capital Q and minus Q here, plus Q and minus Q, which are put on the inner and outer conductors. To calculate potential difference, I must calculate the electric field, which we have done before, but let me recall, I take a Gaussian surface of a spherical Gaussian surface of radius r centered at the center of the inner conductor sphere, and so by symmetry, as we have seen before, the electric field lines are all radial pointing away from the center. So, the electric flux is equal to 4 pi r square into E. E is a radial electric field, and so it is 4 pi r square into E, and the charge contained is capital Q. So, by Gauss's law, we have 4 pi r square E is equal to Q by epsilon 0, or electric field is equal to Q by 4 pi epsilon 0 r square. And because the electric field is radial, I will write this as r cap. So, that is the electric field which we have already seen before. The electric field of the spherical conductor here is exactly like that of a point charge at the center of the spherical conductor. Please note here that the outer conductor is also charged, but the electric field of the outer conducting charge is 0 inside this volume. The only electric field that exists here is because of the positive charge here. The outer charges do not contribute to the electric field within, but the electric field lines are starting from the inner conductor and ending on the outer conductor. So, once having calculated the electric field, I can now calculate the potential difference. So, V is equal to minus integral R B to R A E dot d r, which is equal to integral q by 4 pi epsilon 0 r square d r R A to R B, which is equal to q by 4 pi epsilon 0 minus of 1 by r A to R B, which is equal to q by 4 pi epsilon 0 1 by R A minus 1 by R. And I can write this as V is equal to q by 4 pi epsilon 0 R B minus R A by R A R B. So, that is the potential difference between the inner and outer conductors. Capital Q is the charge carried by the conductors. So, the capacitance of this device C is equal to Q by V, which is equal to 4 pi epsilon 0 R A R B by R B minus R A. So, that is the capacitance of this spherical capacitor. So, the spherical capacitor has an inner sphere conductor, spherical conductor of radius R A, surrounded by an outer spherical conductor of radius R B. Both conductors carry the same amount of charge capital Q, and this particular device forms a capacitor with a capacitance of this value, and this gives me the capacitance of this configuration. I can also look at the following situation, where if I let the radius of the outer conductor go to infinity, if I let the radius R B go to infinity, that is radius of the outer conductor go to infinity, I will get the capacitance of a single sphere of charge of radius R A. So, limit R B tending to infinity, capacitance becomes 4 pi epsilon 0 into R A. That is the capacitance of a single sphere, conducting sphere of radius R A. The other conductor, which is supposed to be carrying negative charges, as infinite size. So, that is the capacitance of a sphere. So, as an example, let us look at a sphere spherical capacitor with R A is equal to 1 millimeter and R B is equal to infinity. So, C is equal to 4 pi epsilon 0 R A, which is equal to 10 to the minus 3 by 9 to the 10 power 9, which is about 0.11 picofarad, which is actually 0.11 into 10 to the minus 12 farad. So, that is the capacitance of a sphere of radius 1 millimeter. So, if I put a charge of 1 picocoulomb, then the voltage generated V is equal to Q by C, which is equal to 10 to the minus 12 by 0.11 into 10 to the minus 12, which is about 9 volts. So, if I put 1 picocoulomb of charge on this sphere of spherical conductor of radius 1 millimeter, I will develop a voltage of 9 volts, and you can, beyond this point, you can calculate what is the electric field of this spherical capacitor, etc., etc. I leave that problem to you, and you can calculate this. In fact, I can also calculate the electric field, the capacitance of a large object like the earth. So, capacitance of the earth So, to do this we assume the earth to be spherical, the radius of the earth is 6,371 kilometers, and so the capacitance is equal to 4 pi epsilon 0 into the radius, which is equal to 6.371 into 10 to the power 6 by 9 into 10 to the power 9, which is about 7.08 into 10 to the minus 4 farad, which is actually 708 microfarad. So, that is the capacitance of the earth. Such a large object as the earth has a capacitance of about 700 microfarads. So, you can imagine that farad is actually a very large unit, and typically we are dealing with picofarads and nanofarads and or microfarads of capacitance. So, as we have seen in the 3 examples, the parallel plate capacitor, the cylindrical capacitor and the spherical capacitor, the capacitance of these devices is a purely geometric quantity determined by the size, shape and separation between the pair of conductors which form the capacitance. So, in principle you can calculate the capacitance of different kind of configurations, but we will restrict to these 3 configurations because you can actually numerically analytically evaluate these numbers. Otherwise, if you have more complex geometries, one would have to do a numerical simulation to calculate the capacitance. Now, in many situations I would need capacitance of certain values in circuit design, as you will see later on in some of your later studies, but I may have capacitance of only certain known values. So, how do I form capacitance of other numbers, other values? So, I can use capacitances in parallel or in series. So, what I want to do is to study now capacitances or capacitors connected in series and in parallel. So, I can actually connect many capacitors either in series or parallel. So, for example, series would imply that I have one capacitor here, another capacitor here, another capacitor here. These are the 2 points. So, I can have capacitor C1, capacitor C2, capacitor C3. So, this is a series connection, they are all in series one after the other. I can have also a situation where I have a capacitor like this, another capacitor like this, a third capacitor like this. So, C1, C2, C3. So, these are the points which are connecting, these are capacitors in parallel. In fact, I can mix these 2 configurations, I can have some capacitors in series, some capacitors in parallel. So, the objective is now to find out what is this equivalent to, what kind of capacitance is equivalent to. So, I would like to replace all the 3 capacitors, this device consisting of 3 capacitors by a single equivalent capacitor. So, my objective now is to calculate what is the equivalent capacitor of a series of capacitors connected in series or a series of capacitors connected in parallel, and we will look at an example which actually contains both such configurations. So, let me look at first capacitors connected in series. Capacitors connected in series. So, let me redraw the figure again here. So, I have one capacitor, another capacitor, another capacitor, and the way we charge the capacitor is to connect a battery. So, please remember the battery is drawn with 2 unequal lines and the capacitors are all drawn with 2 equal lines. So, let me call this capacitance C1, this capacitance C2, this capacitance C3. Let me denote by the voltage across the capacitance V1, voltage is V2 here and voltage is V3, and V is the voltage applied by the battery. So, the potential difference between these 2 points must be total V. So, what I get immediately is the potential difference V must be equal to V 1 plus V 2 plus V 3. V 1 is the potential difference between these 2 points, V 2 is the potential difference between these 2 points, V 3 is the potential difference between these 3 points, these 2 points. So, the potential difference between these 2 points, which is essentially the potential difference between the 2 terminals of the battery, is V 1 plus V 2 plus V 3. So, if I add the potentials, I will get the total potential difference between the 2 terminals of the battery, which is what I have as V. So, we want to understand what happens when the battery is connected to the capacitors. So, we have this is the positive side of the battery, this is the negative side. So, the positive side is connected to the upper plate of this capacitor C1, which is then connected to C2, which is connected to C3. So, let us see what happens when the battery is connected. The positive charge of the battery pulls electrons from the upper plate of the capacitor C1, and so the upper plate of the capacitor C1 gets charged positively. So, this induced positive charge actually creates a negative charge on the lower plate of the capacitor C1. Now, this negative charge on the lower plate of C1 is actually created by pulling electrons from the upper plate of C2, which then gets positively charged, and this one then makes the lower plate of C2 to have negative charges, and this negative charge now pulls the electrons from the upper plate of C3 and leaves it positively charged, which then makes the lower plate of C3 to be negatively charged. So, let us see what happens. So, as soon as I connect the positive side of the battery to the capacitor C1, the positive side pulls electrons from the upper plate, leaving net positive charge on the upper plate of capacitor C1, which then makes the lower plate of C1 to have negative charges, which are coming from the upper plate of C2, which then leaves the upper plate of capacitor C2 to be positively charged. Then that makes the lower plate of C2 to have negative charges, which then makes the upper plate of C3 positively charged and the lower plate of C3 negatively charged. So, what is now happening is that let us now try to see what happens in this part of the circuit, which I draw by a dashed dotted line here. Now, in this part of the circuit, look here that the lower plate of C1 and the upper plate of C2 are connected to each other through this conducting wire, and they are not connected to any part of the circuit, any other part of the circuit. So, the net charge within this must be equal to 0. So, whatever charge you have here must have the same but opposite charge on the lower plate, and this charge is actually equal to the charge on the upper plate of the capacitor C1, and so whatever charge has been supplied by the battery, which is plus q here, is also inducing a minus q on the lower plate. So, if this is plus q here, this is minus q on the lower plate of the capacitor C1, which then induces plus q on the upper plate of C2, which then induces minus q on the lower plate of C2, which then induces plus q on the upper plate of C3, and finally minus q on the lower plate of C3. So, what has actually happened is the battery has only supplied a charge q, and that charge q is now the same in all the capacitors C1, C2 and C3. So, the net charge supplied by the capacitor is only q. And this charge is the same in all the capacitors because they are connected in series. So, let us see what happens. This battery, when I connect the positive charge of the battery, positive terminal to the capacitor, then it induces positive charge here, it pulls electrons from the upper plate, it induces it gives a charge plus q on the upper plate, which then induces the minus q on the lower plate, which then has a plus q on the upper plate of C2, which has a minus q on the lower plate of C2, a plus q on the upper plate of C3 and a minus q on the lower plate of C3. So, please note here that all the capacitors are carrying the same charge q, which is the charge supplied by the battery. So, if each of the capacitors has a charge q, then I can write the following equation for the voltages across each capacitor. So, I have called V1 as the voltage across this capacitor, V2 is the potential difference across this capacitor, V3 is the potential difference across this capacitor. So, this capacitor has a charge q, a capacitor C1 and a voltage V1. So, V1 must be equal to Q1 by Q by C1, V2 which is the potential difference across this plate of the capacitor, V2 must be equal to Q by C2, and similarly V3 the potential difference across this capacitor must be V3 is equal to Q by C3. So, the total potential difference is V1 plus V2 plus V3. Each of the capacitance has a voltage V1 which is Q by C1, V2 which is Q by C2, and V3 which is Q by C3, and where C1, C2, C3 are the 3 capacitors, and as I have used the fact that all the capacitors have the same charge Q supplied to them, and this is the D charge supplied by the battery. So, with these two equations, this equation and this equation, I can combine to form an equation which tells me the overall capacitance of the device. V is equal to V1 plus V2 plus V3, which is equal to Q by C1 plus Q by C2 plus Q by C3. So, I want to replace this by, so what I am trying to do is to find out the equivalent capacitance. So, I have these 3 capacitors here. So, C1, C2, C3 potential V. So, I am trying to find out what is that capacitor which is equal to this. If I call this capacitance C, what is the value of C for which this and this are exactly equivalent? So, this is V and the charge is Q. So, this capacitance C must be equal to Q by V, and I can get from, so this I can use this equation to find out V by Q is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and as you can see here C is Q by V. So, this is equal to 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So, if you have 3 capacitors in parallel in series like this, the total capacitance or the equivalent capacitance of this is actually 1 by C1 plus 1 by C2 plus 1 by C3 and inverse of that. So, 1 by C, which is C is the equivalent capacitance, is 1 by C1 plus 1 by C2 plus 1 by C3. So, for example, if I had a capacitance of 10 microfarads and a capacitance of 2 microfarads connected like this, the total capacitance will be such that I have 1 by C is equal to 1 by 10 plus 1 by 2, which is equal to 12 by 20. So, C is equal to 20 by 12. So, this is all microfarads. So, the capacitances add in such a fashion through this kind of equation. So, given any sequence of capacitance which are connected in series, I can calculate the equivalent capacitance. So, I can actually write a generalized equation which is the following. So, if I had n capacitors connected in series, the equivalent capacitor is equal to sigma I is equal to 1 to n 1 by C I. So, which is actually equal to 1 by C1 plus 1 by C2 plus 1 by C, that is the total capacitance. So, I can use this formula to calculate the capacitance of a series of capacitors which are connected in series. Now, I want to discuss what happens to capacitances connected in parallel. So, let me consider the following circuit here. So, I have so C1, C2, C3, V is the potential applied across the 3 capacitors. The 3 capacitors are connected in parallel. You can see that the potential difference between these 2 points is V, between these 2 points is V, and these are all connected by conductors. So, this is also V, this potential difference is also V. So, all capacitors have a potential difference of V. Now, let me assume charge on C1 is equal to Q1, charge on C2 is equal to Q2 and charge on C3 is equal to Q3. So, please remember in this case the potentials across all the capacitors are the same, but this battery has to supply a charge Q1 to this capacitor, a charge Q2 to this capacitor and a charge Q3 to this capacitor. So, the total charge supplied by the capacitor by the battery Q is equal to Q1 plus Q2 plus Q3, and we know that because I have assumed that the potential the charge the charge Q1 is on capacitor C1, Q2 is on C2, Q3 is on C3. I have the following three equations. I have Q1 is equal to C1V, Q2 is equal to C2V and Q3 is equal to C3V. Same potential, different capacitors at different charges. So, I get Q is equal to C1 plus C2 plus C3 into V. So, now as before, if I want to replace the three parallel capacitors by a single capacitor. So, I have the three capacitors here. So, I want to make it equivalent to a single capacitance C. So, this is C1, C2, C3, V is the potential difference, Q is the charge on the supplied by the battery. So, C must be equal to Q by V, sorry, small q. So, I can use these two equations to get the capacitance, equivalent capacitance C as C1 plus C2 plus C3. So, when I connect capacitances in parallel, three capacitances in parallel, the total capacitance is C1 plus C2 plus C3. If I connect the same capacitances in series, the net capacitance is C, which is 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So, the way the capacitors add to give an equivalent capacitance depends on the way you connect them. So, in general, for n capacitors in parallel, C is equal to sigma I is equal to 1 to n C I. The total capacitance is simply the sum of the capacitance of each of the capacitor. So, if in the earlier example I had taken two capacitors of capacitances 10 microfarads and 2 microfarads. So, if I were to connect them now in parallel, so this is 10 microfarad and this is 2 microfarad, the total capacitance C is equal to 10 plus 2 . So, by this configurations you can actually achieve capacitances which you want in a circuit by putting capacitances which you have in parallel or in series, and you can have multiple combinations to achieve capacitances that you desire. So, to look at another example in which I want to show you that it is possible that in a circuit there are capacitances both in series and parallel. So, let me look at the following example. So, I have the following circuit. So, I have one capacitor here, then I have two capacitors, so this is C1, C2, C3. So, now it is a more complicated circuit. I have these two capacitors are in parallel and this combination is now in series with the other capacitor. So, my problem is now to find out what is the equivalent capacitance of this. That means, what is the capacitance between these 2 points. So, what I will do is I can use the discussion that we have had. First, what I will do is I will use the parallel, these 2 capacitors to be in parallel and equate this to another circuit where I have C1 and another capacitor here. So, I will replace these 2 capacitors by an equivalent capacitor here. So, I have C1 and let me call it C23. So, first I look at the parallel combination and find the equivalent capacitor. This equivalent capacitor is now in series with this capacitor. So, this becomes equal to a capacitor C. So, these 2 are in parallel to give me an equivalent capacitor C23, then C23 is in series with C1 to get me the total capacitance C, equivalent capacitance between these 2 terminals. So, let me try to apply this. So, first let me calculate C23. So, to calculate C23, remember these C2 and C3 are in parallel. So, C23 must be equal to C2 plus C3. Remember parallel capacitors add up like this. So, the equivalent capacitor C23 is C2 plus C3. So, what I get is this equivalent device now here. So, this is C1 and this is C2 plus C3. So, the equivalent capacitor now C is equal to is given by 1 by C is equal to 1 by C1 plus 1 by C2 plus C3. So, I can solve this equation to get me equivalent capacitor. So, let me take the following example. So, let me take C1 is equal to 25 microfarad, C2 is equal to 5 microfarad and C3 is equal to 20 microfarad. So, C23 is equal to C2 plus C3 which is 25 microfarad. So, this parallel combination of C2 and C3 gives me one equivalent capacitor which has a capacitance of 25 microfarad. So, now I have is a series combination of 25 microfarad, another 25 microfarad, and remember that for series I have 1 by C is equal to 1 by C1 plus 1 by C23 which is equal to 1 by 25 plus 1 by 25 which is equal to 2 by 25. So, C is equal to 25 by 2 which is 12.5 microfarad. So, this combination of circuits in which I had this was 25 microfarad, C2 was 5 microfarad and C3 was 20 microfarad. The equivalent capacitance of this configuration is actually 12.5 microfarad. So, this configuration will behave as if there was a capacitance of 12.5 microfarad. So, please note I have been able to generate a 12.5 microfarad capacitance by adding capacitances of 25 microfarad, 5 microfarad and 20 microfarad in such a combination that I get 12.5 microfarad. I will leave the problem to you. You can actually exchange these capacitances in different combinations and find out what are the all possible capacitances that you can generate with these 3 capacitance. For example, you can have all 3 of them in series, all 3 of them in parallel, 2 of them in series and 1 in parallel and parallel to the other one, etc., etc. So, I leave the problem to you. You please try to find out all kinds of combinations of these 3 capacitors which can lead you to different capacitance values, and that will give you an indication of how I am able to generate different capacitances from these 3 capacitances. Now, let me continue with the same problem and find out the following. So, I have this capacitance here and I had these 2 capacitances. So, this was C1, C2, C3. Now, let me assume I apply a potential difference of 10 volts. So, V is equal to 10 volts. So, I want to calculate how much charge are there, how much is the charge in each of these capacitors and what are the potential differences. So, what is the charge supplied by the capacitor by the battery? Q is equal to the net capacitance times the voltage, which is 12.5 microfarad to 10 volts, which is equal to 125 microcoulomb. So, the battery has supplied 125 microcoulomb to charge these capacitors. Now, this 125 microcoulomb will get distributed among the various capacitors. So, I want to find out what are the various charges in the 3 capacitors and what are their potential difference. So, what is the potential difference between these 2 points, what is the potential difference between these 2 terminals of the capacitor and so on. So, first I see is let me calculate this potential difference. So, 125 microfarad has been supplied to this plate. So, this plate also has 125 microfarad. So, V 1 must be equal to Q by C 1. C 1 is the capacitance of this capacitor. So, I have the charge supplied by the battery is 125 microcoulomb, which is supplied to these 2 plates, and this 125 microcoulomb generates a potential difference of Q by C 1, which is 125 10 to the minus 6 by capacitance was 25 microfarad, which is equal to 5 volts. So, if you have applied 10 volts across these 2 terminals, but out of this 5 volts gets dropped across this capacitance, and then of course, the remaining 5 volts must be across these 2, because this difference is 10 volts. So, these 2 capacitance have a potential difference of 5 volts across their terminals. So, I can now calculate what is the charge on each of those. So, Q2 is equal to C 2 into V. So, C 2 was 5 microfarads into 5 volts, which is 25 microcoulomb, and Q 3 is equal to C 3 into V, which is 20 into 10 to the minus 6 into 5 volts, which is 100 microcoulomb. So, see what happens is now. So, I have, let me draw the diagram here. So, I have these 2 and I have these 2 here, these 2 plates. So, there is so if I connect, so I have 125 microcoulomb here. There is so this is C 1, this was C 2 and this is C 3. So, there is 25 microcoulomb here and there is 100 microcoulomb. So, these two totally have 125 microcoulomb, which is actually the same as the charge contained in the upper capacitor. So, the battery has actually supplied 125 microcoulomb, and out of which there is a potential drop of 5 volts here and there is a potential drop of 5 volts between these 2 remaining capacitors. So, you see that given a configuration of capacitors, I can use the law for adding capacitors connected in series or in parallel and find the equivalent capacitor. From there I can calculate the potential difference across each capacitor, the charge contained in each capacitor, and all that I need as far as the capacitance values are concerned. So, this is a very nice way to resolve these problems in containing capacitors. So, you can actually try different kinds of capacitances and I will give you one problem here which you may like to analyze. Consider a parallel plate capacitor as shown. So, you have 2 conducting plates separated by distance d. So, this is my capacitor. Now, what I do is a solid metallic slab of thickness d by 2 is inserted between the two plates without touching them. So, it is like this. So, I put a plate now, this is conducting of width d by 2. The question is, what is the capacitance before insertion and after insertion? The area of the plates is A. The next topic which I would like to discuss is, I will briefly introduce now and then we will continue the discussion in the next class, is energy stored in a capacitor. So, as I mentioned to you in the beginning, capacitors are used as devices which store electrostatic energy. So, when you charge a capacitor, you do work to create an electric field within the plates of the between the plates of the capacitor, you move the charges around and charge the capacitor. So, once you charge the capacitor and disconnect the battery, you have stored some energy within the capacitor, and that energy that you have stored can be released at any time later on whenever you need. So, this is what happens in various applications. For example, if you look at the flash that you use in a camera, there is a capacitor which gets first charged from your battery, and that capacitor, once it gets charged, suddenly releases the charge through the bulb of the flashlight, which then flashes and gives you an illumination for taking your photograph. So, that is an example. So, similarly, you have a large number of examples where you need a sudden release of electrical current through a circuit, and there you can use these capacitors. First of all, you charge them and discharge them whenever you need. So, what I would like to do is to calculate what is the energy stored in a capacitor. So, the charging process develops a potential difference between two capacitors. So, let me assume some general capacitor like this. So, I have plus q here and minus q here, and so you can see here there are electric field lines will be generated between these two capacitor plates, etc. So, I want to calculate what is the energy stored in the capacitor. So, what I will do in the next class is to start from this point, calculate what is the work done in moving charges, electrons from the positive to the negative terminal, and calculate the energy that is required to charge the capacitor from having no charges in the two capacitors to having plus q and minus q, and we will calculate that energy, and I will show you that that energy is also related to the energy contained in the electrostatic field between the two conductors. Okay, so, we will do this in the next class. Thank you very much.